Hello, friend. Welcome back. Or maybe, welcome for the first time. Either way, I'm glad you're here. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's the light remembering where it came from. Tonight I want to tell you a story, not a loud one, not a hurried one, just a quiet drift through time and space following something impossibly small, impossibly old, and impossibly beautiful. A photon, a single particle of light, born in fire, traveling through emptiness, and ending at last in the warmth of your gaze. What if the light touching your skin right now began its journey before you were born? What if it's older than nations, older than language, older than the oldest trees still standing? What if every sunset you've ever seen was a letter written in a furnace 15 million degrees hot, delivered across 93 million miles of nothingness, just to say you are here and the universe sees you? Before we begin, though, let me say this softly. If you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell. Not for noise, but so the next quiet night can find you again. That's all. No rush, no pressure, just an invitation. Now, let's drift. Imagine for a moment that you could follow a single photon from the moment of its birth to the instant it touches your eye. Imagine you could trace its path backward through atmosphere, through void, through time itself, until you arrived at the place where all light begins, the core of the sun. A place so hot, so dense, so impossibly violent that atoms themselves cannot hold their shape. A place where matter becomes energy, where hydrogen kisses hydrogen, and from that collision light is born. This is where our story starts, not here, not now, but there, then, in the furnace. The sun you see is not what it seems. From Earth it looks gentle, warm, a golden disk hanging in the sky, predictable and kind. But that kindness is a lie told by distance. The sun is not gentle, it is a nuclear forge, a star made of chaos, held together only by its own crushing gravity. And at its heart, something extraordinary happens every single second. Deep inside, in a sphere about the size of Jupiter, compressed to unimaginable densities, the temperature reaches 15 million degrees Celsius. 15 million. At that temperature, hydrogen atoms move so fast they overcome the electromagnetic force that normally keeps them apart. They collide. They fuse. 4 hydrogen nuclei become 1 helium nucleus. And in that transformation, something remarkable occurs. The helium weighs slightly less than the 4 hydrogens that created it, just a tiny bit less, about 0.7%. And that missing mass, it doesn't disappear, it becomes energy, pure energy. Einstein told us how. E equals mc squared. Energy equals mass times the speed of light squared. It sounds like math, but it's poetry. It means that locked inside every atom is a fire waiting to be lit. And inside the sun, that fire never stops burning. Every second the sun converts about 600 million tons of hydrogen into helium. And in that process, 4 million tons of matter simply vanish, not destroyed, transformed into light, into heat, into the energy that makes life on Earth possible. 4 million tons. Every second. And the sun has been doing this for 4.5 billion years. Think about what that means. The sun is literally burning itself away, atom by atom, converting its own substance into the light that warms your face. And yet, it's so massive, so abundant with fuel that it can afford to do this for another 5 billion years before it runs out. The sun is patient, impossibly patient. It gives without counting the cost. But here's the part that makes you pause, the part that makes the night feel deeper. That photon, that single particle of light, born in the fusion of hydrogen, doesn't leave immediately. It can't. Because the sun is not hollow, it's dense. so dense that light itself cannot escape easily. Every few millimeters, the photon collides with another particle, an electron, a proton, a helium nucleus, and every time it collides, it changes direction, bounces, scatters. Scientists call this a random walk. The photon doesn't know where it's going. It has no memory, no map, no sense of up or down. It just moves, hits something, changes direction, and moves again, over and over and over. And this process, this endless wandering through the sun's interior, takes time. Not seconds, not minutes, not even years. It takes somewhere between 100,000 and 200,000 years. Let that settle in your mind for a moment. 100,000 years. The photon that touches your skin today was born before humans learned to farm, before we built the first cities, before we looked up at the stars and gave them names. It has been stumbling through the darkness inside the sun, trying to find its way out for longer than recorded history. The distance from the sun's core to its surface is only about 700,000 kilometers. If light could travel in a straight line, it would take just over 2 seconds. But it can't. The sun's interior is too crowded, too chaotic. And so, the photon wanders, a sleepwalker in a forest of glass, stumbling, forgetting its path, stumbling again. And as it wanders, it transforms. It starts as a gamma-ray photon, the most energetic, most violent form of light. But with every collision, it loses a little energy. Gamma becomes X-ray. X-ray becomes ultraviolet. Ultraviolet becomes visible light. By the time it finally reaches the surface, it has softened. It has learned to whisper. If the sun released its gamma rays directly, life on Earth would be impossible. We'd be sterilized in an instant. But the sun doesn't do that. It tempers its own violence. It forces every photon to slow down, to scatter, to lose its edge, until what finally escapes is warm, gentle, safe. The kind of light that makes flowers grow. The kind of light that lets you see. There's something almost tender in that. Don't you think the universe's most violent process filtered through time and distance and endless collision until it becomes the golden glow of a late afternoon? The light that paints clouds at sunset. The light that right now is reflecting off these words and entering your eyes. And all of this patient chaos happens in a place we will never visit. The core of the sun is unreachable. No spacecraft can go there. No instrument can measure it directly. We know it exists only because of mathematics, because the light that escapes tells us a story about where it's been. Every photon is a messenger. Every ray of sunlight a postcard from the furnace. So, the next time you feel warmth on your skin, remember, that warmth is old, ancient. It survived 100,000 years of wandering just to reach this moment, just to touch you, just to remind you that the universe is still burning, still generous, still finding ways to give. But the photon's journey is not over, not yet. It has escaped the chaos of the core, yes. It has drifted through the radiative zone, through the churning convective zone, through all the layers of the sun's hidden interior. And now it stands at the threshold. The photosphere, the visible surface, the place where trapped becomes free. One more step and it will leap into the void, into the silence, into the 8 minutes that will carry it across space toward a small blue planet towards you. The heart of the sun is a place of impossible extremes, a furnace where the rules of ordinary matter break down, where atoms are stripped bare, where gravity crushes with such force that particles have no choice but to merge. And in that merging, in that violent, beautiful collision, light is born. Let's go deeper. Let's stand in our imagination at the very center of the sun, not at the surface where we can see the golden glow, but at the core, the place where it all begins. The core is small, relatively speaking, only about 1/4 of the sun's radius. If the sun were the size of a beach ball, the core would be about the size of a grapefruit. But packed into that grapefruit is nearly half of the sun's total mass. That's how dense it is. Scientists estimate the density at about 150 grams per cubic centimeter. For comparison, water is 1 gram per cubic centimeter. Lead is about 11. The core of the sun is denser than any material you've ever touched, denser than anything that exists naturally on Earth. And the temperature, 15 million degrees Celsius. That number is so large it stops meaning anything to our everyday experience. You can't compare it to a hot summer day, or a blast furnace, or even the surface of molten lava. It's in a category all its own. At 15 million degrees, atoms as we know them cannot exist. The electrons that normally orbit the nucleus are ripped away by the sheer violence of thermal motion. What's left is a plasma, a sea of naked nuclei, mostly hydrogen and free electrons, all moving at incredible speeds. Hydrogen is the simplest element, just one proton, sometimes with a neutron attached, making it deuterium-heavy hydrogen. But mostly it's just protons, and these protons are electrically charged, positive, and like charges repel. Under normal circumstances, two protons will never get close enough to touch. The electromagnetic force pushes them apart. It's one of the fundamental forces of nature, and it's strong, very strong. But in the core of the sun, normal circumstances don't apply. The temperature is so high that protons are moving at about 500 kilometers per second, 500,000 meters every second. And there are so many of them packed so tightly together that collisions are inevitable. Most of the time, the protons just bounce off each other. The electromagnetic repulsion wins. They get close, feel the push, and veer away. But every once in a while, very rarely, two protons get close enough that another force takes over. The strong nuclear force. It's the strongest force in nature, but it only works at incredibly short distances. You have to get the protons within about 1 femtometer of each other. That's 1 quadrillionth of a meter, closer than close. And when you do, the strong force grabs hold, and suddenly the protons stick together. This is nuclear fusion. And it's not a simple process. It happens in steps. First, two protons collide and fuse, but the combination is unstable. Almost immediately, one of the protons converts into a neutron, releasing a positron and a neutrino. What's left is deuterium, heavy hydrogen. 1 proton, 1 neutron. And in that conversion, energy is released. Not as light, not yet, but as kinetic energy. The particles fly apart, carrying heat. Then the deuterium nucleus collides with another proton. They fuse. Now you have helium-3. 2 protons, 1 neutron. Still not stable enough. Still not the end. Finally, 2 helium-3 nuclei collide and fuse, creating helium-4, the stable form of helium, 2 protons, 2 neutrons. And in that final step, 2 protons are released free to start the process over again. This chain of reactions is called the proton-proton chain, and it's the primary way the sun generates energy. There are other fusion pathways, more complex ones, involving carbon and nitrogen as catalysts, but the proton-proton chain dominates. And the net result of all these collisions and conversions is that 4 hydrogen nuclei become 1 helium nucleus, and the helium weighs less than the hydrogen, about 0.7% less. Where did the missing mass go? It became energy, and not just a little energy, a lot. Because of Einstein's equation, E equals mc squared. The speed of light squared is a huge number, about 90 quadrillion, so even a tiny amount of mass converts into an enormous amount of energy. When the sun fuses 4 hydrogen nuclei into 1 helium nucleus, it releases about 26 million electron volts of energy. That might not sound like much, but multiply it by the number of fusion reactions happening every second, and you get something staggering. The sun fuses about 600 million tons of hydrogen into helium every second. 600 million tons. Imagine a mountain range. Imagine the Rocky Mountains. Now imagine converting that entire mass into energy in 1 second. That's what the sun does. Every second. And in that conversion, 4 million tons of matter are completely transformed into pure energy. 4 million tons. Vanished. turned into light heat neutrinos, the fire that keeps the sun burning. And here's where the photon enters the story. Most of the energy from fusion is released as kinetic energy, the motion of particles, but some of it is released as gamma rays, high-energy photons, born in the instant when nuclei collide and rearrange. These gamma rays are not gentle. They're not the kind of light you can see or feel. They're pure violence, wavelengths measured in picometers, energies measured in millions of electron volts. If a gamma ray from the sun's core could somehow reach your body, it would tear through your cells, ripping apart DNA, ionizing atoms, destroying the delicate chemistry that keeps you alive. But gamma rays don't reach you, not from the core, because they can't escape. Not directly. The core of the sun is surrounded by the radiative zone, a thick shell of plasma that extends about 70% of the way to the surface. And in the radiative zone, the density is still enormous, not as high as the core, but high enough that photons can't travel freely. Every few millimeters, a gamma-ray photon collides with an electron, or a nucleus. And when it collides, it's absorbed. The particle takes in the photon's energy, vibrates, and then re-emits a photon, but not necessarily the same photon, not necessarily with the same energy, and definitely not in the same direction. This is the beginning of the photon's long, slow journey. It's born as a gamma ray in the core, but within milliseconds it's absorbed and re-emitted, again and again, each time losing a little energy, each time changing direction. Gamma becomes X-ray. X-ray becomes ultraviolet. The photon softens step by step, collision by collision, as it drifts outward through the radiative zone. And the journey is not quick. Scientists have calculated that it takes between 50,000 and 100,000 years for energy born in the core to reach the surface. 50,000 years. That's longer than human civilization, longer than the oldest written records. The light you see today, the sunlight warming your face, began its journey before humans built the pyramids, before we domesticated animals, before we learned to plant crops. Let me give you another way to think about this. The sun produces energy at a rate of about 3.8 times 10 to the power of 26 watts. That's 380 septillion watts. More energy in 1 second than all of humanity has used in its entire existence. And all of that energy starts as fusion in the core. But it doesn't burst out instantly. It seeps out, slowly, patiently, filtered through layer after layer of dense plasma, until what finally emerges is warm, gentle, life-giving light. There's a reason for this slowness. If the sun could release its energy instantly, if there were no radiative zone to slow things down, the sun would explode. It would blow itself apart in a matter of minutes. The radiative zone acts as a buffer, a throttle. It regulates the flow of energy, ensuring that the sun burns steadily, consistently for billions of years. Without it, we wouldn't be here. There would be no Earth, no life, just a brief, brilliant flash, and then nothing. But the sun is patient. It holds its fire. It forces every photon to wander, to scatter, to wait. And in that waiting, the photon transforms. By the time it nears the top of the radiative zone, it's no longer a gamma ray. It's visible light, yellow, orange, red, the colors of the spectrum we can see, the colors that don't kill us. And then, the photon enters the convective zone, the outermost 30% of the sun's interior. Here the temperature has dropped to about 2 million degrees, still unimaginably hot, but cool enough that radiation alone can't carry the energy. The plasma begins to convect. Hot plasma rises, cool plasma sinks. Like water boiling in a pot, the sun churns. And the photon caught in these currents rides upward, faster now, more directed. The convective zone is quicker than the radiative zone. The photon might spend only a few thousand years here instead of 50,000. But even here, even in the rising currents, the photon still collides, still scatters. The plasma is still dense. There are still countless particles in the way. The photon is not yet free, not yet able to move in a straight line. It's still trapped, still wandering, still waiting for the moment when the density finally thins enough to let it go. And that moment is coming. The photon is approaching the photosphere, the surface, the boundary between sun and space. Just a few hundred more kilometers, just a few more collisions. And then, at last, release. The leap into the void. The beginning of the journey we think we know. The 8 minutes across 93 million miles of emptiness. But before that leap, before that freedom, the photon must survive one final transformation. It must cross from the convective zone into the photosphere where the temperature drops to a mere 5,500 degrees and the plasma finally thins enough to let light escape. And in that crossing, the photon will carry with it the memory of the furnace, the echo of fusion, the heat of 100,000 years of wandering. The nuclear forge has done its work. The photon is born, tempered, ready, and now it rises toward the light. The photon is born, and immediately it's lost. Not lost in the sense of missing, not wandering aimlessly with no destination, but lost in the sense that it has no map, no compass, no memory of where it came from or where it's going. Just endless collision, endless redirection. A maze with a trillion walls and every wall made of atoms that refuse to let light pass. This is the part of the story most people never hear. We talk about sunlight traveling from the sun to Earth in 8 minutes. We mention that number with confidence as if the journey is simple, straightforward, a straight shot across the void. But we forget the waiting. We forget the stumbling. We forget that before the photon ever sees the stars, it must first escape the sun itself. And that escape takes not minutes, not hours, not years, but millennia, tens of thousands of years. Maybe 100,000, maybe more. The sun is not hollow. It's not a balloon of fire with empty space inside. It's dense, unimaginably dense, a sphere of plasma so tightly packed that light cannot move freely. And our photon, freshly born in the core, as a gamma-ray burst of pure energy, immediately encounters resistance. Not a wall, not a barrier, just matter, everywhere, inescapable. Let me give you a sense of what the photon faces. The core of the sun, where nuclear fusion happens, has a density of about 150 grams per cubic centimeter. That's about 150 times denser than water. If you could scoop out a teaspoon of the sun's core and bring it to Earth, it would weigh about as much as a bowling ball. And in that density, atoms don't exist the way they do here. The temperature is so high, 15 million degrees Celsius, that electrons are stripped away from nuclei. What's left is plasma, a soup of protons, neutrons, electrons, and helium nuclei, all moving at incredible speeds, colliding constantly. And the photon moving at the speed of light cannot avoid them. Every few millimeters it hits something, an electron, a proton, a helium nucleus. And when it hits, it doesn't bounce off cleanly like a billiard ball. It's absorbed completely. The particle takes in the photon's energy, holds it for a fraction of a second, maybe a microsecond, maybe less, and then re-emits a new photon. Not in the same direction, not with the same energy, but in a random direction. Up, down, sideways. Sometimes even back toward the core, undoing any progress the photon might have made. This is what physicists call a random walk. And it's not a metaphor. It's a precise mathematical description of a process with no memory and no direction. Imagine you're standing in the middle of a vast dark room. You take a step in a random direction. Then another step, random again. Then another. If you take enough steps, millions of steps, billions of steps, you'll eventually drift away from where you started. But the path you take will be wildly inefficient. You'll double back. You'll cross your own trail. You'll wander in circles. And the distance you travel will be vastly longer than the straight line distance from start to finish. That's what happens to the photon. The distance from the sun's core to its surface is only about 700,000 kilometers. If the photon could travel in a straight line, It would escape in less than a second, less than 1 second, but it can't. And so instead, it wanders for 100,000 years, maybe longer. Some estimates go as high as 200,000 years, or even 1 million, depending on the path the photon takes, the number of collisions it endures. Let's do the math. Scientists estimate that a photon born in the sun's core will undergo somewhere between 10 to the power of 24 and 10 to the power of 26 collisions before it reaches the surface. That's somewhere between 1 septillion and 100 septillion collisions. Each one a reset, each one a gamble, each one erasing any sense of direction the photon might have had if photons could have such a thing. And here's the part that feels almost cruel. The radiative zone, the layer of the sun where most of this wandering happens, is only about 300,000 kilometers thick. If you could walk that distance at a steady pace, never stopping, you'd cover it in about 7 years. If you could drive at highway speed, you'd cross it in about 4 months. But the photon traveling at the speed of light takes 50,000 to 100,000 years. Because it's not traveling in a straight line, it's bouncing, scattering, taking a step forward, 2 steps back, 1 step sideways, over and over and over again. There's a way to visualize this. Imagine you're trying to escape a forest, but it's not a normal forest. It's a forest where the trees are packed so tightly that you can't see more than a few feet in any direction. And every time you take a step, you bump into a tree, and you have to choose a new direction at random. You might head north, then east, then south, then west. And even though the edge of the forest is only a mile away, it might take you years to find it because you keep looping back, retracing your steps, getting turned around. That's the photon's experience. Except the forest is made of plasma, and the trees are made of protons and electrons, and the photon is moving at the speed of light, but getting nowhere fast. Like a sleepwalker in a forest of glass, the photon stumbles, forgets its path, and stumbles again. And as the photon wanders, something else happens. It loses energy, not all at once, just a little bit with every collision. It starts as a gamma-ray photon, the most energetic form of light, with wavelengths measured in picometers, trillionths of a meter. But every time it's absorbed and re-emitted, there's a chance it'll come out with slightly less energy. Gamma becomes X-ray. X-ray becomes ultraviolet. Ultraviolet becomes visible light. By the time the photon reaches the top of the radiative zone, it's no longer the violent burst of energy it was at birth. It's been tamed, softened. The voice learning to whisper after screaming for tens of thousands of years. And this is important. If the sun released gamma rays directly from its core, life on Earth would be impossible. We'd be sterilized instantly. Every living cell would be torn apart by high-energy radiation. But the sun doesn't do that. It forces every photon to wander, to collide, to downgrade, until what finally escapes is gentle, safe, the kind of light that makes grass grow and skin tan and eyes see color. The sun protects us by refusing to let its light escape too quickly, by making it wait, by making it soften. Now, here's something most people get wrong. They think light travels from the sun to Earth in 8 minutes, and they stop there. They forget the 100,000 years that came before. They forget the waiting. And when you point this out, when you say, actually, the light you're seeing started its journey 100,000 years ago, they're surprised, shocked even, because it doesn't match the story they have been told. The story that sunlight is fast, immediate, always fresh. But it's not. Sunlight is ancient, older than human civilization, older than the pyramids, older than agriculture, older than the last ice age. The photon touching your face right now began its journey when Homo sapiens were still learning to make stone tools, when our ancestors were living in small bands hunting mammoth and painting on cave walls in France and Spain. That light is older than any human structure, older than any written word. It's a time traveler carrying energy from an era we can barely imagine. Think about that. The warmth you feel on your skin is ancient. It survived 100,000 years of chaos just to reach this moment, just to touch you, and we barely notice. We take it for granted. We assume the sun is always new, always fresh, always immediate. But the sun is patient, impossibly relentlessly patient. Eventually, after wandering for eons, the photon drifts into the convective zone. This is the outer 30% of the sun's interior, and here the rules change. The temperature has dropped to about 2 million degrees Celsius, still unimaginably hot, still plasma, but cool enough that the sun can no longer transport energy purely through radiation. Instead, it uses convection. Hot plasma rises, cool plasma sinks. Like water boiling in a pot, the sun churns. Giant convection cells, each one the size of Texas, or larger, roll and bubble and carry heat toward the surface. And the photon caught in these rising currents gets carried along. You'd think this would speed things up. And it does a little. The convective zone is faster than the radiative zone. The photon might spend only a few thousand years here instead of 50,000, but it's still not free. Because even in the convective currents, even as the plasma rises and falls, the photon still collides, still scatters, still changes direction. The churning helps, yes. It gives the photon a lift, a direction, a current to ride. But it doesn't solve the fundamental problem. The sun is too dense. There are too many particles. And light, for all its speed, cannot slip through the cracks because there are no cracks. There is only endless overlapping matter. And here's a strange thought. By the time the photon reaches the top of the convective zone, it's not really the same photon anymore. Not technically. Because every time a photon is absorbed and re-emitted, it's a new photon. The original gamma-ray photon born in the core was destroyed within milliseconds of its creation. What we're following now is not that photon, but its descendant, its great-great-great-grandchild, septillions of generations removed. The energy is the same, the journey is the same, but the identity. That's a question physics can't quite answer. Is it the same photon if it's been absorbed and re-emitted a septillion times? Or is it a lineage of photons, each one carrying the story forward? Philosophically, it's fascinating. Practically, it doesn't matter. The energy that began in the core eventually reaches the surface. That's what counts. And now, after 100,000 years of wandering, of stumbling, of patient, relentless chaos, the photon approaches the photosphere, the visible surface of the sun, the boundary between trapped and free. The density thins, the collisions grow less frequent, the temperature drops to a mere 5,500 degrees Celsius, and the photon for the first time in its long, strange existence finds space, room to move, room to breathe if photons could breathe. It doesn't hesitate. It doesn't look back. There's no ceremony, no fanfare, just a final scattering, a final redirection, and then something changes. The plasma ahead is thinner, transparent almost, and the photon, with one last collision, one last change of direction, breaks free. Patience written in light, time dissolved in the dark. And now, after waiting longer than empires last, the photon leaps toward the surface, toward the corona, toward the void beyond, ready at last to begin the part of the journey we think we know. The photon stands at the edge of everything it has ever known. Behind it, 100,000 years of chaos. Ahead, the void. And between them, one final barrier, the photosphere, the sun's skin, the place where trapped becomes free. This moment, this crossing from surface to space, is not dramatic. There are no explosions, no fanfare. Just a photon slipping through the last thin veil of plasma, and suddenly everything changes. The collisions stop. The scattering ends. For the first time since its birth, the photon moves in a straight line. And the universe, vast and cold and silent, opens before it like an infinite road. But before we follow it into that emptiness, let's linger here, at the surface. Because this is where transformation completes. This is where violence becomes warmth, where gamma becomes gold. The photosphere is only about 500 kilometers thick. By cosmic standards, that's nothing. Thinner than Earth's atmosphere. A whisper of a boundary. But it's the only part of the sun we can actually see. When you look up at the sun, please don't. But if you did, you're not seeing the core. You're not seeing the radiative zone or the convective zone. You're seeing this, the photosphere. A layer of gas so thin, it's almost not there, glowing at about 5,500 degrees Celsius. Hot enough to vaporize any metal. Hot enough to make rock boil. But compared to the core's 15 million degrees, it's practically cool. It's the sun learning to be gentle. And here's what happens in that final 500 kilometers. The photon, which has spent eons transforming, completes its metamorphosis. It sheds the last of its violence. When it entered the photosphere, it might have been ultraviolet, energetic, invisible to human eyes. But as it passes through, as it interacts with the hydrogen atoms still clinging to the sun's surface, it loses just a bit more energy. It redshifts. It softens. And by the time it emerges, it's visible light, yellow, the color we associate with sunlight, the color that makes everything on Earth look the way it does. Scientists describe this as black body radiation. The sun, despite being a nuclear furnace, glows the same way any hot object glows. Heat something up enough, and it emits light. The hotter it is, the bluer the light, the cooler the redder. At 5,500 degrees, the sun glows yellow-white, not because it chose to, not because yellow is special, but because that's what physics demands at that temperature. If the sun were hotter, it would look blue like the star Rigel. If it were cooler, it would look red like Betelgeuse. The sun's color is just a thermometer, a translation of heat into wavelength. But here's something people often get wrong. They think the sun is yellow because we see it as yellow, but that's not quite true. The sun actually emits light across the entire visible spectrum. Red, orange, yellow, green, blue, violet. All of it. When you mix all those colors together, you don't get yellow. You get white. The sun is white, or very close to it. We perceive it as yellow because Earth's atmosphere scatters some of the blue light away, leaving the yellows and reds to dominate. But an astronaut in space looking at the sun through a properly filtered visor would see it as it truly is. White, pure, the color of every color combined. And that's what the photon carries. Not a single color, but a spectrum. A range of energies all packed into one tiny massless particle. When we say a photon of sunlight, we're really talking about billions of photons each with its own wavelength, its own frequency, its own tiny story. Some are red, some are violet. Most are somewhere in between. And they all escape together, a flood of light pouring from the photosphere. 63 million watts per square meter, relentless as rain. Let me give you a number that might help. Every second the sun's surface releases about 3.8 times 10 to the power of 26 watts of energy. That's 380 septillion watts. More energy in 1 second than humanity has used in its entire history. More energy than all the coal ever burned, all the oil ever pumped, all the nuclear reactions ever harnessed. And it does this every second, without effort, without thought, just because that's what stars do. And yet, only a tiny, tiny fraction of that energy ever reaches Earth. The sun radiates in all directions equally, a sphere of light expanding outward at 300,000 kilometers per second. And Earth, from the sun's perspective, is just a dot. We intercept less than 1/billionth of the sun's total output. 1/billionth. And that 1/billionth is enough to power every ecosystem, every weather pattern, every breath of wind and drop of rain. Imagine what the other 999,999,999 parts are doing, spreading out into the universe, touching planets and moons and asteroids, or touching nothing at all, just traveling forever into the dark. Now think about this. If the photon had kept its original energy, if it had somehow escaped the sun as a gamma-ray photon instead of visible life on Earth would be impossible. Gamma rays are deadly. They tear through DNA. They ionize atoms. They destroy cellular structure. A single gamma-ray photon carries enough energy to disrupt the delicate chemistry that makes life work. But the sun doesn't release gamma rays not from its surface. It tempers them. It forces them to scatter, to lose energy, to downgrade, until what finally escapes is safe, warm. The kind of light that makes leaves turn green and skin turn brown and eyes see color. The sun protects us by slowing its own light down, by making it wander, by refusing to let it escape until it's learned to be kind. There's something almost parental in that, isn't there? A star that could kill us with its full strength, choosing instead to soften, to filter, to give us only what we can survive. But not all stars are so gentle. Blue giant stars, much hotter than the sun, emit more ultraviolet light, more X-rays. If Earth orbited a blue giant, our atmosphere would be stripped away in a geological instant. We'd be sterilized. Red dwarfs, cooler stars, emit mostly infrared, less visible light. A planet orbiting a red dwarf would be dim even at noon. The sun sits in a sweet spot. Not too hot, not too cold, just right. And that's not a coincidence. Life emerged on Earth partly because the sun is the kind of star that allows it. We are in a very real sense children of the sun's specific temperature. And here's another layer. The photosphere isn't smooth. It's not a perfect glowing shell. If you could zoom in, if you could see it up close, you'd notice it's covered in granules, convection cells, bright centers where hot plasma rises, dark edges where cool plasma sinks. Each granule is about 1,000 kilometers across, roughly the size of Texas. And they boil, they churn. They rise and fall in cycles that last about 8 minutes. The sun's surface is alive with motion. A slow, endless churning, like the surface of a pot of oatmeal, but made of ionized gas and light. And sometimes the photosphere erupts. Solar flares, coronal mass ejections, massive bursts of energy that send billions of tons of plasma hurtling into space at millions of kilometers per hour. These eruptions are triggered by the sun's magnetic field, which twists and tangles in the convective zone, and sometimes snaps, releasing energy in an instant. When that happens, the photons don't drift out gently. They're blasted out, thrown. And if Earth happens to be in the way we see auroras, the northern lights, the southern lights, curtains of green and red and violet dancing in the sky as those high-energy particles collide with our atmosphere and make it glow. But our photon, the one we're following, isn't part of a solar flare. It's just an ordinary photon, one of the trillions upon trillions released every second in the quiet, steady glow of the photosphere. It doesn't know it's ordinary. It doesn't know it's one of many. It just knows if a photon can know anything, that the way ahead is clear. And so it goes. Out, away. Through the chromosphere, a thin layer of gas just above the photosphere glowing faintly red. Through the corona, the sun's outer atmosphere, a halo of superheated plasma that somehow paradoxically is hotter than the surface itself. Scientists still aren't entirely sure why the corona is so hot. Millions of degrees even though it's farther from the core. It defies intuition. But the photon doesn't care. It passes through in milliseconds, unaffected, untouched, already traveling faster than anything else that has mass could ever hope to move. And then silence. True silence. The kind of silence that only exists in space. No air, no particles to vibrate, no sound. Just the photon alone moving through the void at exactly 299,792,458 meters per second. The speed of light, the universal speed limit, the fastest anything can go, and also strangely the slowest light can move. Because in a vacuum, light doesn't accelerate. It doesn't build up speed. It simply is that fast from the first instant forever. Do you ever wonder what it feels like to be that fast? Of course you can't. Speed is relative. You need something to compare it to. But from the photon's perspective, if it had one, there is no journey. Einstein showed us this. Time dilation. At the speed of light, time stops. A photon experiences no duration between its emission and its absorption. It leaves the sun and arrives at Earth in the same subjective instant, even though we measure 8 minutes passing. The photon doesn't wait. It doesn't travel. It simply exists at both ends of its path simultaneously. And we trapped in slower time are the ones who perceive the gap. It's beautiful in a way, and strange. We think of light as something that moves, but maybe it doesn't. Maybe we move and light just is. The photosphere fades behind it now. The sun shrinks, though not quickly. At this distance, just a few thousand kilometers out, the sun still fills half the sky. But with every second, it grows smaller, dimmer, more distant. And the photon, free at last, begins the crossing. 93 million miles, one astronomical unit. The space between fire and life. The gap that took 100,000 years to prepare for and will take only 8 minutes to cross. And in that crossing, the photon will see things we can only imagine. Emptiness, stillness, the pure patient dark. Empty is not the same as nothing, and the space between the sun and Earth is the most perfect empty you'll ever try to imagine. No air, no sound, no dust worth mentioning, just distance, pure, patient, absolute distance. And in that distance, the photon travels alone, not slowing, not stopping, not thinking because it can't, just moving the way water moves downhill, the way time moves forward, inevitable, uninterrupted, free. This is the part of the journey we think we understand. 8 minutes and 20 seconds from the sun to Earth. Everyone knows that number. It shows up in textbooks, documentaries, casual conversations about space. But knowing the number isn't the same as feeling what it means. So, let's slow down. Let's spend some time in the void. Because even nothing has a story worth telling. The photon left the photosphere traveling at 299,792,458 meters per second. That's the speed of light in a vacuum, and it's not an approximation. It's exact, defined. In 1983, scientists decided to stop measuring the speed of light and instead use it to define the meter itself. 1 meter is now officially the distance light travels in 299,792,458 of a second. We built our measurement of space around light's constancy. That's how fundamental this speed is. That's how much we trust it. And in the vacuum between the sun and Earth, light never wavers. It doesn't speed up when it's far from the sun's gravity. It doesn't slow down when Earth's gravity starts to pull. It just moves. Constant, relentless. The universe's heartbeat steady as stone. Now, let's talk about the distance. The sun and Earth are separated by about 93 million miles. Or, if you prefer kilometers, 150 million. Astronomers call this distance one astronomical unit. 1 AU, and they use it as a measuring stick for the solar system. Mercury is 0.4 astronomical units from the Sun. Mars is 1.5 astronomical units. Jupiter is 5.2 astronomical units. It's a convenient number. A human-scale way of talking about distances that are otherwise incomprehensible. But 93 million miles is still hard to grasp. So, let me try to give you a sense of it. If you got in a car and drove toward the sun at 60 miles per hour, never stopping, never slowing, you'd arrive in about 177 years. If you took a commercial jet, flying at 500 miles per hour, you'd get there in about 21 years. If you were on the fastest spacecraft humans have ever built, the Parker Solar Probe, which at its peak reaches speeds of 430,000 miles per hour, as it dives toward the sun, you'd still need about 9 days to cover the distance. 9 days. For something moving faster than anything we've ever made. But the photon doesn't take 9 days. It takes 8 minutes and 20 seconds. And that's because nothing, absolutely nothing, moves faster than light. Not rockets, not particles, not information, not even gravity. Light sets the speed limit for the universe, and everything else is just trying to keep up. Here's a thought experiment. Imagine the sun suddenly disappeared, vanished, gone. What would happen? You might think Earth would immediately fly off into space, no longer held by the sun's gravity. But that's not what would happen. Gravity, like light, travels at the speed of light. The gravitational influence of the sun would continue to hold Earth in orbit for 8 minutes and 20 seconds after the sun disappeared. And in those same 8 minutes and 20 seconds, we'd still see the sun shining in the sky. The light that left before the disappearance would still be on its way. For 8 minutes, we'd orbit a star that no longer existed, bathed in light from a source that was already gone. And then, all at once, darkness and chaos. The light would vanish, the orbit would break, and Earth would drift. Of course, the sun isn't going to disappear. But the thought experiment shows you something important. Light isn't instant. It takes time. And in that time, the universe can change. Now, here's where things get strange. From our perspective sitting here on Earth, the photon's journey takes 8 minutes and 20 seconds. We can measure it. We can set a timer. We can watch the clock tick. But from the photon's perspective, the journey takes no time at all. Zero, not a short time, not a fast time, no time. This is what Einstein's theory of relativity tells us. The faster you move, the slower time passes for you. And at the speed of light, time stops completely. The photon doesn't experience duration. It doesn't age. It doesn't wait. It leaves the sun and arrives at Earth in the same instant, at least from its own frame of reference. This is hard to wrap your mind around, I know. How can something take 8 minutes and also take no time? The answer is that time is not absolute. It's not a universal river that flows the same for everyone. It's relative. It depends on your speed, your gravity, your perspective. For us, time passes. For the photon, it doesn't. Both are true, both are real, and the universe doesn't see a contradiction. And here's another layer. Because the photon is moving so fast, space itself contracts. From the photon's perspective, the distance between the sun and Earth isn't 93 million miles. It's zero. Length contraction. Another consequence of relativity. The faster you move, the shorter distances become in the direction you're traveling. And at light speed, all distances collapse to nothing. The photon doesn't cross a gap. There is no gap. The sun and Earth are, from the photon's point of view, in the same place. So the photon's journey, the one we're spending all this time talking about, doesn't exist for the photon itself. It's a journey only we perceive, only we measure. The photon is born and absorbed in a single timeless moment, and everything in between is just the universe's way of keeping things from happening all at once. But let's come back to our perspective, because for us, those 8 minutes are real. And in those 8 minutes, the photon is truly alone. Space between the sun and Earth isn't completely empty, of course. There's the solar wind, a stream of charged particles, mostly electrons and protons, flowing out from the sun at about 1 million miles per hour. But even the solar wind is sparse. In the densest regions, you'd find maybe 10 particles per cubic centimeter. That's 10 particles in a space the size of a sugar cube. For comparison, the air you're breathing right now has about 25 quintillion molecules per cubic centimeter. The solar wind is so thin, it might as well not be there. And the photon doesn't interact with it anyway. Photons don't collide with electrons or protons the way they collide with atoms in the sun's interior. They can be absorbed or scattered, yes, but only if they hit just right. And in the vast emptiness of space, the odds of hitting anything are almost zero. The photon flies through the solar wind like a ghost through a wall, untouched, unbothered, alone. There are other things in the space between the sun and Earth. Dust grains, tiny fragments of rock and ice, leftovers from the solar system's formation. But they're even rarer than the solar wind. You'd have to search a volume the size of a building to find a single grain. And again, the photon almost certainly misses them. Space is so empty that emptiness is its defining feature. And yet, the photon isn't invisible. If you could be out there floating in the void between the sun and Earth, you'd see light everywhere. The sun would be blazingly bright, a point of light so intense you couldn't look at it directly. And the photons streaming past you, billions of them every second, would be heading in all directions. Some toward Earth, some toward Venus, some toward Mars. Most toward nothing, just spreading out into the infinite dark, traveling for years, centuries, millennia, until maybe they hit something, or maybe they never do. Maybe they travel forever. Here's a humbling thought. Most of the light the sun produces will never be seen, never be absorbed, never warm a planet or illuminate a moon. It will just go out into the galaxy, past the Kuiper belt, past the Oort cloud, into interstellar space. And billions of years from now, some of those photons might pass near another star, might enter another solar system, might against all odds strike the surface of another world. Light from our sun, carrying a message from a time when humans still existed, delivered to a place we'll never see. But our photon, the one we're following, has a destination. It's aimed by pure chance at a small blue dot, a planet, the third rock from the sun. And in just a few more minutes, it will arrive. As the photon travels, Earth grows larger, not quickly, not dramatically, but steadily. At first, it's just a point of light reflecting the sun's glow. Then it becomes a disk. Then it shows color, blue, white, brown, green, the colors of oceans, clouds, continents, forests, the colors of life, and the photon still moving at the only speed it knows closes the distance. 90 million miles, 80 million, 70, 60, 50. The numbers count down, but the photon doesn't notice. It doesn't slow. It doesn't prepare. It just is. And here's something people often forget. Light doesn't arrive all at once. It's not like flipping a switch. The light you see from the sun right now left 8 minutes and 20 seconds ago. But the light you see 1 second from now left 8 minutes and 21 seconds ago. There's a continuous stream, a river of photons, each 8 minutes behind the event that created it. The sun you see is always the past. You've never seen the sun as it is right now. None of us have. We only ever see where it was, what it was doing 8 minutes ago. And if something dramatic happened on the sun, a flare, an explosion, we wouldn't know until the light arrived. The universe has a speed limit, and that means the universe has a delay. Information even carried by the fastest thing there is takes time to travel. So when you look up at the sun, you're not just seeing light, you're seeing time. You're seeing the past preserved in photons delivered across the void. And now the photon is almost there. Earth looms ahead, growing larger with every passing second. The atmosphere comes into view, a thin blue shell wrapped around the planet's surface. And the photon, which has traveled for 100,000 years through the sun and 8 minutes through the void, is about to face its final test. The air, 78% nitrogen, 21% oxygen, 1% everything else. A barrier thinner than an eggshell, but dense enough to scatter light, to bend it, to change it one last time before it reaches the ground. The photon touches air, and everything changes. For 100,000 years, it wandered through plasma. For 8 minutes, it flew through perfect emptiness. But now, it meets something new. Something thin, yes. Something fragile. But dense enough to scatter. Dense enough to bend. Dense enough to paint the sky blue and turn sunsets red. The atmosphere, Earth's shield, Earth's canvas, and the photon's final obstacle before it finds your eyes. This is where light becomes color, where invisible becomes visible, where physics becomes beauty. Let's start at the edge, the Kármán line, 100 kilometers above Earth's surface. This is the boundary most scientists use to mark where space ends and atmosphere begins. It's arbitrary, of course. There's no wall, no sign, just a gradual thickening of air molecules as you descend. But by the time the photon crosses this invisible line, it's no longer alone. There are particles here, nitrogen molecules, oxygen molecules, sparse at first, just a few per cubic meter. But with every kilometer downward, the density doubles, then doubles again, then again. And the photon, which has moved unhindered for 8 minutes, suddenly finds itself in a crowd. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and 1% everything else. Argon, carbon dioxide, water vapor, trace gases. And all of these molecules are small, very small. A nitrogen molecule, 2 nitrogen atoms bonded together, is about 0.3 of a nanometer across. That's 3/10 billionths of a meter, impossibly tiny. But the photon's wavelength, the distance between its peaks, is about 500 nanometers. Visible light, human-scale light. And when something that small encounters something that tiny, strange things happen. The photon doesn't bounce off air molecules the way a ball bounces off a wall. It interacts. The electromagnetic field of the photon disturbs the electrons in the molecule. The electrons oscillate. And when electrons oscillate, they re-emit light. Not always in the same direction. Not always with the same energy. Sometimes the photon passes straight through. Sometimes it scatters. And the color of the light, the wavelength, determines which happens more often. This is called Rayleigh scattering, named after Lord Rayleigh, a British physicist who worked it out in the 1870s. He discovered that shorter wavelengths, blue and violet light, scatter much more than longer wavelengths, red and orange. The exact relationship is inversely proportional to the 4th power of the wavelength. That sounds complicated, but it just means this. If you double the wavelength, the scattering decreases by a factor of 16. Blue light with a wavelength around 450 nanometers scatters almost 10 times more than red light, with a wavelength around 700 nanometers. And that's why the sky is blue, not because the ocean is blue and reflects upward. That's a common mistake, and it's backwards. The ocean looks blue because it reflects the sky. The sky is blue because air scatters blue light more than red. When sunlight enters the atmosphere, the blue wavelengths bounce around, scatter in all directions, fill the sky. And no matter where you look, as long as you're not looking directly at the sun, you see that scattered blue. A sky painted by physics, a ceiling colored by the size of molecules. But here's something interesting. Violet light scatters even more than blue. So, why isn't the sky violet? 2 reasons. First, the sun produces less violet light than blue. Its peak output is in the green part of the spectrum, but it emits plenty of blue and less violet. Second, and more importantly, human eyes are less sensitive to violet. We have 3 types of cone cells in our retinas. 1 sensitive to red, 1 to green, 1 to blue. The blue cones do respond to violet, but not as strongly. So even though there is violet light scattered in the sky, we perceive it as blue. The color of the sky is not just physics, it's biology too. Now, let's follow the photon deeper. As it descends through the atmosphere, the air grows thicker. At 10 kilometers altitude where commercial jets fly, the air pressure is about a quarter of what it is at sea level. At 5 kilometers, it's half. At sea level, there are roughly 25 quintillion molecules per cubic centimeter. That's 25 followed by 18 zeros. In every breath you take, you inhale more air molecules than there are stars in the observable universe. And every single one of those molecules is a potential scattering site for light. The photon, statistically speaking, will scatter multiple times before it reaches the ground, maybe 3 times, maybe 10. Each scattering redirects it, changes its path, but it doesn't lose energy, not from Rayleigh scattering. That's elastic scattering. The photon comes in with a certain wavelength and leaves with the same wavelength. It just changes direction. Blue light stays blue, red stays red. The atmosphere sorts light by color, but it doesn't change the colors themselves, except when it does, because there's another kind of scattering, me scattering. This happens when light interacts with particles larger than its wavelength, dust, pollen, water droplets. These particles don't preferentially scatter blue over red. They scatter all wavelengths roughly equally. And that's why clouds are white. The water droplets in clouds are much larger than the wavelength of visible light, so they scatter all colors together. White light in, white light out. A cloud is just a mass of tiny mirrors bouncing light in every direction without caring about color. But back to our photon. Let's say it's a yellow photon, right in the middle of the visible spectrum. It enters the atmosphere at a steep angle nearly straight down. This is midday. The sun is high. And the photon's path through the atmosphere is relatively short, maybe 20 kilometers from the edge of the atmosphere to the ground. It scatters a few times, but not enough to lose its direction. It's heading down, and eventually it will hit something. The ground, a tree, a building, you. But let's change the scenario. Let's say the photon enters the atmosphere at a shallow angle. This is sunset. The sun is near the horizon, and now the photon's path through the atmosphere is much longer, maybe 300 kilometers. It has to pass through the thickest part of the atmosphere, the part closest to the ground where the air is dense and full of particles. And as it travels that long, shallow path, something happens. The blue light scatters away. All of it. Every blue photon that enters the atmosphere at sunset scatters so many times that it never makes it through. It bounces up sideways back towards space. Only the red and orange and yellow photons, the ones that scatter, less survive the journey. And that's why sunsets are red. Not because the sun changes color, not because the air itself is red, but because the blue has been filtered out, scattered away, leaving only the warm colors behind. This is the same reason the sun looks yellow during the day and orange at sunset. In space, the sun is white, but seen through Earth's atmosphere, especially near the horizon, the blue wavelengths are removed. What's left skews toward red. The sun's true color is hidden by the very air that lets us breathe. And here's a piece of history. For centuries, people didn't understand why the sky was blue. Aristotle thought it was because the air itself was slightly blue, a faint color that became visible when you looked through enough of it. Leonardo da Vinci believed the blue came from water vapor in the air. Even Isaac Newton, who discovered that white light could be split into colors, didn't quite solve the puzzle. It wasn't until Lord Rayleigh worked out the mathematics of scattering that we understood. The sky is blue because molecules are small and light is a wave, simple, elegant, true. But there's more. The atmosphere doesn't just scatter light, it also absorbs it. Certain wavelengths are absorbed by certain molecules. Ozone, for instance, absorbs ultraviolet light. That's why the ozone layer protects us. It filters out the high-energy UV that would otherwise damage our DNA. Water vapor absorbs infrared. Carbon dioxide absorbs specific bands of infrared too, which is why it's a greenhouse gas. The atmosphere is not a passive filter. It's an active participant choosing which wavelengths to let through and which to block. And for visible light, the atmosphere is mostly transparent. Most photons make it through, but not all. About 30% of the sunlight that reaches Earth is reflected back into space, by clouds mostly, by ice and snow, by the surface of the ocean at certain angles. This is Earth's albedo, its reflectivity, and it's part of what keeps our planet at the temperature it is. If Earth were darker, it would absorb more light and be warmer. If it were brighter, it would reflect more light and be cooler. The balance is delicate. Now, think about this. Every blue sky you've ever seen, every red sunset, every golden afternoon is the result of trillions upon trillions of photons scattering off molecules you can't see, following rules you didn't know existed, painting the world in colors that are fundamentally accidents of wavelength and size. The sky doesn't try to be beautiful. It just is. And we, with our biology and our brains, look up and call it beauty. There's a question worth asking. If you were on a planet with a different atmosphere, would the sky look different? Yes. Absolutely. Mars, for instance, has a very thin atmosphere, mostly carbon dioxide. And because of dust suspended in the air, the Martian sky looks butterscotch, pinkish orange. during the day. But at sunset on Mars, the sky near the sun turns blue, the exact opposite of Earth. That's because the dust particles scatter red light more at certain angles, and the blue light coming directly from the sun dominates near the horizon, a sky that inverts Earth's palette, a reminder that color is not universal, it's contextual. On Venus, with its thick atmosphere of carbon dioxide and sulfuric acid clouds, the sky is a hazy yellow-orange. On Titan, Saturn's largest moon, with its nitrogen atmosphere and methane haze, the sky is a deep orange, almost rust-colored. Every world has its own sky, its own light, its own way of bending the sun's rays into something new. But here on Earth, the photon has made it through. It has scattered, yes. It has been redirected maybe more than once. But it has survived. It has passed through the stratosphere where ozone absorbs UV, through the troposphere where weather happens, through the boundary layer where the air touches the ground. And now, it's close, so close, just a few meters above the surface, just a few moments from its final destination. But before it can reach your eyes, it must do one more thing. It must touch the world. It must strike something solid, something real, a leaf, a pebble, a wall, your skin. Because light, for all its speed and energy, cannot be seen unless it interacts. It must reflect. It must scatter one last time, and in that final scattering, it will reveal the color of the world. The photon falls, and the world reaches up to meet it. After 100,000 years trapped in the sun, after 8 minutes crossing the void, after scattering through 70 miles of atmosphere, the photon is about to do something it hasn't done since it left the photosphere. It's about to touch matter, real, solid, tangible matter. And in that touch and that final collision, the photon will do something remarkable. It will reveal color, not its own color, but the color of the thing it strikes. Because color, you see, is not a property of objects. It's a conversation between light and surface, a dialogue written in wavelengths. Let me ask you something. What color is a leaf? You'd say green, wouldn't you? And you'd be right, but also wrong, because the leaf isn't green. Not really. Green is what the leaf refuses to be. Here's how it works. White light sunlight contains all the colors of the visible spectrum. Red, orange, yellow, green, blue, violet. Every wavelength mixed together. When that light strikes a surface, some wavelengths are absorbed and some are reflected. The absorbed wavelengths disappear, their energy converted into heat or chemical reactions. The reflected wavelengths bounce off and travel to your eyes, and the color you see is the color that was rejected, the color the object didn't want. A leaf looks green because it absorbs red and blue light and reflects green. Chlorophyll. The molecule that makes photosynthesis possible is incredibly good at capturing red and blue wavelengths. Those are the energies it needs to split water molecules and build sugars. But green light. Green is useless to the leaf, so it bounces off. Wasted, rejected. And that rejection is what we call color. Think about that for a moment. The green of a forest, the emerald of grass, the jade of new spring leaves, all of it is light the plants don't want. The color of life is the color of refusal. And it's not just leaves. Every colored object works this way. A red apple absorbs green and blue reflects red. A blue sky, well, we talked about that. Scattering. But a blue shirt, it absorbs red and green reflects blue. Black objects absorb everything. White objects reflect everything. And if you could see an object that absorbed nothing and reflected nothing, it would be invisible. Perfectly transparent, like air, like glass. But glass is interesting, isn't it? It doesn't reflect all wavelengths equally. It lets most of them pass through. That's what makes it transparent. But even glass reflects a little. About 4% of the light that hits glass bounces off the surface. That's why you can see your reflection in a window. The other 96% passes through bends slightly because glass is denser than air and continues on its way. Refraction, the bending of light as it moves from one medium to another. It's why a straw in a glass of water looks broken, why lenses can focus light, why rainbows form in raindrops. But our photon isn't hitting glass. Let's say it's hitting something simpler. A white wall, white paint. And white paint is just tiny particles of titanium dioxide suspended in a binder. Each particle scatters light. All wavelengths. Equally, no preference. The photon strikes a particle, bounces off. Strikes another, bounces again, and eventually exits the paint, heading in a new direction. Almost all of its energy intact. Almost all of its wavelength unchanged. The wall looks white because it refuses nothing. It reflects everything. A democracy of color. Now, let's change the surface. Let's say the photon strikes a piece of charcoal, black, pure black, and charcoal is porous, coal, full of tiny cavities. When the photon enters one of those cavities, it bounces around inside, hitting the walls over and over. And each time it hits, some of its energy is absorbed. By the time it might escape, if it escapes at all, it's lost most of its energy. The charcoal looks black because it's a trap, a maze with no exit. The photon goes in and it doesn't come out. But black isn't the absence of color. That's a common mistake. Black is the absorption of all colors. It's the presence of everything held so tightly it can't escape. And that's why black objects get hot in the sun. They're absorbing all that light energy and converting it to heat. White objects stay cooler because they reflect most of the light away. This is why wearing black on a sunny day makes you warmer. You're catching light, holding it, turning it into temperature. Here's a question. If color is just reflected, light does color exist in the dark? Think about it. If there's no light, there's nothing to reflect. A red apple in a dark room isn't red. It's nothing, colorless. The redness only exists when light touches it. And even then, the redness exists not in the apple, but in the space between the apple and your eye. Color is not a property. It's an event, a moment, a fleeting interaction between photon and surface. And that means color is subjective, not in the sense that you and I might disagree about what's red, but in the sense that color requires an observer. A photon reflects off an apple. If no one is there to see it, is it red philosophically? That's debatable. Physically, the photon is still the same wavelength, but the experience of redness that requires a brain, requires eyes, requires the entire biological apparatus that turns electromagnetic waves into the sensation we call color. Let's go deeper. Not all surfaces reflect light the same way. A mirror reflects light specularly. That means the angle of incidence equals the angle of reflection. Light comes in at 30 degrees. It leaves at 30 degrees. Smooth, predictable. That's why you can see a clear image in a mirror. Every photon from a particular point on your face bounces off the mirror at the same angle and reconverges in your eye. The mirror preserves the spatial information. It organizes the light. But a rough surface like paper or cloth or skin reflects light diffusely. The surface is covered in tiny bumps and valleys, each oriented in a different direction. A photon hits one bump and bounces off at a random angle. Another photon hits a valley and bounces differently. The light scatters in all directions. That's why you can't see your reflection in a piece of paper. The spatial information is scrambled. The light is still reflected, but it's disorganized, chaotic. And your skin is somewhere in between. It reflects some light specularly, which is why skin can look shiny. But it also reflects diffusely, which is why you don't see a perfect mirror image on someone's face. And underneath the surface, light penetrates a little into the layers of cells, and some of it scatters back out, giving skin a soft, translucent quality. That's subsurface scattering. It's why human skin looks alive, why wax figures and CGI characters sometimes look uncanny. They get the surface reflection right, but they miss the glow from within. Now, let's talk about something people get wrong all the time. The idea that objects have color because they contain colored molecules. That's partially true, but it's not the whole story. Yes, molecules absorb specific wavelengths because of their electronic structure. Chlorophyll absorbs red and blue because its electrons can jump to higher energy states when hit by photons of those energies. But The color you see is the wavelengths that aren't absorbed, the leftovers, the rejects. And here's the strange part. The same object can look different colors under different lights. A red dress under white light looks red, but under blue light, it looks dark, almost black, because there's no red light to reflect. The dress hasn't changed, the light has. And color, remember, is a conversation. Change one side of the conversation and the whole thing shifts. This is why artists care about lighting, why photographers obsess over the color temperature of their lamps, why the same paint swatch looks different in the store and in your living room. Color is not fixed, it's contextual. It's negotiated every single moment between the light that's available and the surface that's receiving it. And then there's fluorescence. Some molecules absorb light at one wavelength and emit it at another. They take in high-energy photons, ultraviolet usually, and spit out lower-energy photons, visible light. That's why highlighter ink glows under a black light. It's absorbing UV, which you can't see, and emitting yellow or green, which you can. The molecule is a translator, a converter, turning invisible into visible. Certain rocks do this. Fluorite, calcite, willemite. Under normal light, they look ordinary. But under UV, they glow. Vivid greens, reds, oranges. It's not magic. It's just chemistry. Electrons absorbing energy, jumping to higher states, and then falling back down, releasing the excess as light. A slow-motion version of what happens in the sun's core, but gentle, quiet, beautiful, and bioluminescence. That's when living things make their own light. Fireflies, certain fungi, deep-sea fish. They use chemical reactions to produce photons directly. No sun needed, no reflection. Just enzymes and molecules rearranging in light as a byproduct. These organisms carry the sun's fire inside them. They are their own stars. But our photon, the one we're following, doesn't need chemistry. It just needs a surface. And let's say it finds one, a simple one, the back of your hand. The photon strikes your skin. Some of it is absorbed, warming you ever so slightly. But some of it reflects, bounces off, scattered by the proteins in your skin cells, by the melanin that gives your skin its tone. And in that reflection, the photon changes direction, one last time, no longer falling, now rising, now heading toward the one thing that can truly see it, your eye. The world you see is not the world itself. It's the light the world chose to let go. Every color is a goodbye, every shadow a secret kept. And the photon, having touched the world, now carries that goodbye towards you. The photon has arrived, but arrival is not the same as being seen. Your eye is open. Light pours in a constant flood, millions of photons every second. And among them, one photon. Our photon. The one born 100,000 years ago in the sun's core. The one that crossed 93 million miles of void. The one that scattered through atmosphere and bounced off your skin. It's here now, just millimeters away. And in the next fraction of a second, something extraordinary will happen. The photon will stop being light, and it will become vision. It will become thought. It will become you. This is the final transformation. Light into chemistry. Chemistry into electricity. Electricity into meaning. And it happens so fast, so seamlessly, that you never notice the miracle of it. Let's start at the surface. The photon approaches your eye. The first thing it encounters is the cornea, a transparent dome of tissue covering the front of your eye. The cornea is about 0.5 millimeter thick, made mostly of water and collagen fibers arranged in a precise crystalline structure. And that structure is key. Collagen fibers are normally opaque. They scatter light. But in the cornea, they're lines so perfectly spaced so evenly that the scattered light interferes destructively. It cancels out. What's left is transparency. The cornea is clear not because it's empty, but because it's organized. Order masquerading as emptiness. And the cornea does more than let light through. It bends it. Refraction. The same phenomenon that makes a straw look broken in water. Light travels slower in dense materials than in air, and when light slows down, it bends. The cornea is curved dome-shaped, and that curvature focuses the light. About 2/3 of your eye's total focusing power comes from the cornea, not the lens. The cornea. Most people don't realize that. The photon passes through bends slightly and enters the anterior chamber, a small space filled with a clear fluid called aqueous humor. It's mostly water with a bit of protein and glucose. The photon crosses this space in nanoseconds, unbothered, unimpeded, and then it reaches the pupil. The pupil is not an object, it's an absence, a hole, the black circle in the center of your iris. And the size of that hole changes depending on how much light is available. In bright light muscles, in the iris contract, making the pupil small. In dim light, the muscles relax, and the pupil dilates. This is automatic, unconscious. Your eye is constantly adjusting, trying to let in just the right amount of light. Too much, and you're blinded. Too little, and you can't see. The pupil is a shutter, a gate, and right now it's open just enough for our photon to slip through. Behind the pupil is the lens, a transparent, flexible structure shaped like a lentil. The lens is suspended by tiny fibers called zonules, and muscles around the lens can change its shape. When you look at something far away, the lens flattens. When you look at something close, the lens bulges. This is called accommodation. It's how your eye focuses on different distances. And unlike the cornea, which is fixed, the lens is adjustable. It fine-tunes the focus. The cornea does the heavy lifting. The lens does the detail work. The photon passes through the lens, bends again, and enters the largest chamber of the eye, the vitreous humor, a clear gel-like substance that fills most of the eyeball. It's about 80% water, with long molecules of hyaluronic acid giving it structure. The photon travels through this gel, and here's something strange. The vitreous humor is not perfectly clear. As you age, proteins in the gel clump together, forming tiny strands and specks. And sometimes when light passes through those specks, cast shadows on your retina. You see them as floaters, little squiggles drifting across your vision. They're harmless. Just the debris of time, the eye aging one floater at a time. But the photon doesn't hit a floater. It keeps going straight through the vitreous until it reaches the back of the eye, the retina, and this is where everything changes. The retina is a thin layer of tissue about 0.5 millimeter thick, lining the inside of the eyeball, and it's one of the most complex structures in the human body. It contains about 130 million photoreceptor cells, cells that can detect light. And they come in two types, rods and cones. Rods are the most numerous, about 120 million of them. They're incredibly sensitive. A single rod cell can detect a single photon. Yes, one. Just one photon is enough to trigger a response. But rods don't detect color. They only respond to brightness. They're your night vision, your peripheral vision. When you're in a dark room and you can barely make out shapes, that's your rods working. They trade color for sensitivity. They see in shades of gray, but they see in almost no light at all. Cones are less sensitive but more sophisticated. There are about 6 million of them, concentrated mostly in the center of your retina in a tiny region called the fovea. And cones come in 3 types, one sensitive to red light, one to green, one to blue. Each type has a different protein, a different opsin, that responds to a different range of wavelengths. And by comparing the signals from all 3 types, your brain can reconstruct color. Red plus green equals yellow. Green plus blue equals cyan. All 3 together equals white. Color vision is not a direct perception. It's a calculation, a comparison. Your brain doing math at the speed of thought. Our photon, let's say, is yellow. It strikes a cone cell in your fovea. And here's where the magic happens. The photon enters the cone, passes through layers of cellular machinery, and reaches the outer segment, a part of the cell packed with stacks of membrane, like a stack of pancakes, and embedded in those membranes are millions of molecules of a protein called photopsin. And photopsin contains a smaller molecule called retinol, a derivative of vitamin A. And retinol is the key. Retinol is a shapeshifter. It exists in two forms. One is bent kinked like a crooked stick, the other is straight. And normally in the dark, retinol sits in the bent form, snugly fitted into the photopsin protein. But when a photon strikes retinol, something incredible happens. The photon's energy causes one of retinol's chemical bonds to rotate. Just one bond, 180 degrees. And in that rotation, the molecule straightens out, from bent to straight, from cis to trans, as chemists say. And that change, that tiny shift in shape, is enough. The straightened retinol no longer fits properly in the photopsin. It pushes against the protein, distorting it, and that distortion triggers a cascade, a chain reaction. The photopsin activates another protein, which activates another, which activates another. And within milliseconds, the signal amplifies. One photon, one molecule of retinol. And suddenly thousands of molecules are responding. The cell's electrical balance shifts. Ions flow across the membrane. And the cone cell, which had been releasing neurotransmitters in a steady stream, suddenly stops. That cessation is the signal, silence, darkness in the constant chatter. And the cells connected to the cone, called bipolar cells, notice the silence. They respond. They pass the signal forward to ganglion cells, which collect signals from many bipolar cells and send them down the optic nerve, a bundle of about 1 million nerve fibers that connects your eye to your brain. And here's something most people don't realize. The signal your brain receives is not light detected. It's light stopped. Your photoreceptors are active in the dark and quiet in the light. Vision is built on absence, on the interruption of a baseline. It's counterintuitive, but it works. The optic nerve carries the signal from your eye to the back of your brain, to the visual cortex, and the journey takes about 13 milliseconds. 13 thousandths of a second. That's how long it takes for a photon to become a thought. Longer than the 8 minutes it took to cross space. Longer than the nanoseconds it took to cross your eye. Because converting light into meaning is hard. It requires chemistry. It requires electricity. It requires layers and layers of processing. And by the time the signal reaches your visual cortex, it's no longer raw data. It's been filtered, compared, contextualized. Your brain doesn't just receive images. It interprets them. It fills in gaps. It makes guesses. There's a blind spot in each of your eyes, the place where the optic nerve exits the retina. No photoreceptors there, just a hole. But you don't see a hole. Your brain fills it in using information from the surrounding area. You see a continuous image even though part of it is fabricated. A lie told so smoothly you never notice. And color. Your brain invents it, not the wavelength. That's real. But the experience of redness, of blueness, of the golden glow of sunset that's constructed. A translation from wavelength into sensation. And different brains might translate differently. There's no way to know if the red you see is the same red I see. We both call it red. We both agree on which things are red. But the internal experience that's locked inside your skull, incommunicable, private. Here's a piece of history. For a long time, people didn't understand how vision worked. Ancient Greeks thought the eye emitted rays that touched objects and brought back information. Vision as reaching out, not as light coming in. It wasn't until the Islamic Golden Age around the year 1000 that a scientist named Ibn al-Haytham figured it out. He argued that light enters the eye, not the other way around. He wrote about lenses refraction the camera obscura. He laid the groundwork for modern optics. And yet, even he couldn't explain how the eye turns light into vision. That required biology, molecular biology, tools that wouldn't exist for another 1,000 years. And even now we don't understand everything. We know the mechanics, photon to retinal to signal to brain, but we don't know how the brain creates the sensation of seeing. How neurons firing in patterns become the experience of color, shape, motion, depth. That's the hard problem of consciousness, and it remains unsolved. But the photon doesn't care about philosophy. It has completed its purpose. It struck retinal. It changed a molecule. It triggered a cascade. And then, having given up its energy, it ceased to be. The photon died the moment it was seen. Its last breath became your first thought. And in that death, in that transformation, you gained something. Awareness, information, a fleeting glimpse of the world as it was 13 milliseconds ago. Every second, 100 million photons enter your eyes. And every second, 100 million tiny deaths occur, each one a spark of vision, each one a whisper from the universe saying, "This is what exists. This is what is real. This is what you can know." Vision is not passive, it's active, aggressive even. Your eyes are not windows, they're interrogators. They capture light, tear it apart, extract its secrets, and discard what's left. And all of this complexity happens so fast you never notice. You open your eyes and the world is just there. Immediate, obvious, but it's not. It's constructed, frame by frame, photon by photon. A continuous act of creation performed by your brain, using light as raw material. Light does not enter the mind, light becomes it. And the photon, having made that final leap, now exists only as a memory, a pattern of neurons, a thought with no name, the end of a journey that began before you were born, delivered at last to you. We've followed a single photon across time and space, from fire to void to thought. And now, here at the end, let's take a moment to look back at the path we've traveled. Because this journey, this quiet drift through physics and biology, is not just the story of one photon. It's the story of every moment you've ever seen, every sunrise, every face, every word on every page, all of it light transformed. The photon we followed was born in the core of the sun, sometime during the late Pleistocene epoch, when our ancestors were still painting on cave walls and following herds across frozen tundra. It wandered through plasma for 100,000 years, colliding, scattering, slowly drifting outward through layers of star stuff, so dense that distance became meaningless and time stretched beyond comprehension. And then finally, it reached the surface, the photosphere, and in an instant, it leapt into space. 8 minutes and 20 seconds. That's all it took to cross the void. 93 million miles at the speed of light. No hesitation, no deviation, just pure, relentless motion through the most perfect emptiness the universe can offer. And as it flew, Earth grew larger, a blue dot, then a disk, then a world, clouds and oceans and continents all waiting to be seen. The photon entered the atmosphere, that thin shell of gas we live beneath and rarely think about, and it scattered. It bounced off nitrogen molecules, changed direction, painted the sky blue. It survived the filtering, the bending, the chaos of air, and it emerged still intact, still carrying the energy it was born with, now aimed at something solid, your skin, a leaf, a wall, whatever surface happened to be in the way. And in that collision, that final reflection, the photon revealed color. Not its own, but the color of the thing it touched. Because objects don't have color, they have preferences. They absorb some wavelengths and reject others, and the rejected light. The unwanted light is what we see. Every color is a refusal. Every hue, a goodbye. Then at last, the photon found your eye. It passed through the cornea, through the lens, through the vitreous gel, and struck a single molecule of retinal buried in a cone cell on your retina. And that molecule, absorbing the photon's energy, changed shape. Just slightly. Just enough. And that change triggered a cascade, a chain reaction, a signal that raced from cell to cell, down the optic nerve into the depths of your brain. 13 milliseconds. That's how long it took for light to become vision, for energy to become awareness. And then the photon was gone, used up, transformed, no longer light but thought, no longer a particle but a memory. The journey ended not in darkness but in you, Do you ever stop to think about how much of your life is built on light? Not metaphorically, literally. The food you eat was grown by plants that captured sunlight and turned it into sugar. The warmth you feel on a summer day is photons transferring their energy to your skin. The colors you see, the faces you recognize, the words you read, all of it depends on light, traveling from source to eye, bridging the gap between world and mind. You are a creature of light. We all are, and yet we take it for granted. We flip a switch and the room brightens, and we never marvel at the fact that we're commanding photons into existence, summoning them from filaments and LEDs, bending them to our will. But natural light sunlight is different. It's not commanded. It's given, freely, endlessly. The sun has been pouring light into space for 4.5 billion years, and it will continue for another 5 billion until it exhausts its hydrogen and swells into a red giant and consumes the inner planets and finally collapses into a white dwarf, a cooling ember fading slowly into the dark. But that's a long time from now. For now, the sun burns, and every second it converts 4 million tons of itself into light. And most of that light will never be seen. It will travel forever out into the galaxy, carrying a message from a star that may one day be forgotten. But some of it reaches us. A tiny fraction. 1/1000th of the sun's total output. And that 1/1000th is enough. Enough to warm the oceans. Enough to power the winds. Enough to grow forests and fill the sky with birds and paint the clouds at sunset in shades of orange and red that make you stop just for a moment and remember that the world is beautiful. Here's something to consider. The light you saw today is older than you, older than your parents, older than the oldest living tree. It began its journey before humans had written language, before we built cities, before we looked up at the stars and wondered what they were. And yet, it arrived here now, in this moment, just in time to let you see. That's not a coincidence. That's not luck. That's just physics. Patient, relentless, indifferent physics. The universe doesn't care if you notice, but it gives you the tools to notice anyway. And the tools are remarkable. Your eyes can detect a single photon. Not reliably, not every time, but the machinery is there. The sensitivity is extraordinary. And your brain processing the signals from 130 million photoreceptor cells can distinguish millions of colors, track motion, perceive depth, recognize faces in a fraction of a second. All of this happens automatically, unconsciously. You don't have to think about seeing, you just see. But the complexity behind that simplicity is staggering. There's a thought experiment I want to share. Imagine you could see individual photons, not as a continuous stream, but one at a time, distinct, separate. What would the world look like? It would flicker, like an old film reel, because light doesn't arrive smoothly. It arrives in packets, discrete chunks of energy. And if your eyes were sensitive enough to detect each one, individually, vision would become a strobe, a stuttering dance of presence and absence. But your brain smooths it out. It integrates the signals over time, creating the illusion of continuity, the illusion of a stable, persistent world. But the world isn't stable. It's a storm of photons, a blizzard of light, and we see it as calm only because our brains are very, very good at lying. And here's the strangest part. Some of the photons entering your eyes right now are older than the sun. Not many, just a few. But they exist. Photons from distant stars, stars that died billions of years ago. Their light only now reaching Earth. When you look up at the night sky, you're not seeing the universe as it is. You're seeing it as it was. The light from the nearest star, Proxima Centauri, left 4 years ago. The light from the Andromeda Galaxy left 2.5 million years ago. You're looking into the past, always. And the deeper you look, the further back you see. Telescopes are time machines, not metaphorically, literally. They show us the universe as it was preserved in light, delivered across eons. But even the light from the sun, our closest star, is 8 minutes old. You've never seen the sun as it is right now. None of us have. We see where it was, what it was doing 8 minutes ago. And if the sun were to suddenly vanish, we wouldn't know for 8 minutes. We'd still see it shining, still feel its gravitational pull. And then, all at once, darkness, chaos. The light would stop, the orbit would break, and we'd drift into the cold, wondering what happened, looking up at a sky that no longer made sense. Of course, the sun isn't going to vanish, but the thought experiment reveals something important. The universe has a speed limit. Information even carried by light takes time to travel, and that means the present is fractured, layered. What's happening here and now is not the same as what's happening on the sun or on Mars or in another galaxy. The universe doesn't have a universal now. It has a patchwork of nows, each one separated by the time it takes for light to cross the gap. Simultaneity is an illusion, and light is the thing that keeps the illusion from falling apart. So where does that leave us? We've traveled with a photon from birth to death, from the nuclear forge at the heart of the sun to the chemical cascade in the retina of your eye. A journey measured not just in distance but in time. 100,000 years and 8 minutes and 13 milliseconds. And at the end of it, what do we have? Vision, awareness, the simple, quiet miracle of being able to see. Light is not just a tool, it's a connection, a bridge between the universe and the mind, between the distant and the intimate, between what is and what we perceive. And every time you open your eyes, you're participating in that connection. You're catching light, holding it, turning it into meaning. You are in a very real sense made of light, not literally, but experientially. Your awareness, your sense of the world, is built from photons, from packets of energy that traveled across the void just to show you what exists. And that's worth pausing for, isn't it? Worth feeling grateful for, even if just for a moment. The next time you see the sun, remember the journey. Remember the 100,000 years of wandering. Remember the 8 minutes of silence. Remember the 13 milliseconds of transformation. And know that the light touching your face is not new. It's ancient. It's patient. And it's still, after all this time, finding its way home. We've drifted through fire, void, and thought. We've traced the path of something so small it has no mass and yet carries all the energy of the universe. We've seen how light becomes color, how color becomes vision, how vision becomes the world you know. And maybe you'll look at light a little differently now, not as something ordinary, not as something to take for granted, but as something extraordinary, something worth noticing, something worth being amazed by, because every photon has a story. Every beam of light is a message, and the universe, vast and cold and mostly empty, is still, after billions of years, still finding ways to show us it's there, still lighting the way, still giving us something to see. The journey never truly ends, you know. Maybe every ending is just light starting again, born in a star, crossing the dark, finding an eye, becoming a thought, and then perhaps inspiring another thought, another question, another quiet moment of wonder. The photon dies, but the story continues. In you, in everyone who looks up and sees. So, tonight when you close your eyes and let the darkness come, remember this. The light will still be there, waiting, traveling, ready to begin again when you're ready to see. The sun will rise, the photons will fall, and the world, patient as always, will be there to meet them. Thank you for drifting with me through this journey, for lending me your time, your attention, your willingness to wonder. If you found something here worth keeping, something that made the world feel a little more miraculous, then the light has done its job, and so have we. Until the next quiet night finds us, rest well. Dream gently. And when you wake, may the light be kind to you. Good night.